Okay, everybody, welcome back to week 2 of Energy 241. Alternative fuels. And just a couple notes here as we get started. If you take a look at the Moodle shell on here, I know not everybody's had a chance to get their books yet. If you look right in here in topic 1, you'll see chapters 1 through 5 of the textbook. They're here in a PDF, so you can use those until you get your book, whether you order it off the Amazon or get the Kindle e-version of it. There was one textbook in the Missoula College Library. It has been checked out by one of the students, so you can check around, see if you can find another copy, but as far as I know, they only have the one copy. But it's easy enough and much cheaper actually to get it online than what it was to buy it here in the bookstore. Another thing about that, we are in week 2 already, and if you look in week 1, topic 1, here in the middle there was a quiz. Some of you have not taken that quiz yet. Please take that quiz, get it knocked out so we can get it graded and get you started on this. Now being into week 2, week 1 we talked about alternative fuels in general and more about the history of how we got into our carbon-based fossil fuel usage. So week 2, topic 2, we're going to jump right into vegetable oils as one of our alternative fuels that we're looking at, and how we can use that and how that integrates with the system that we have today. So looking at chapter 2, which all I did was download it from up here in topic 1. And there it is. And you see this is straight out of the textbook, exactly what you'd see if you had the textbook. We kind of need to address what is the fuel being used for. And typically what you find is right here in the first paragraph, when we look to generate electricity, the usual fossil fuel that we look towards is coal, because electricity is generated at one place and then transported through power lines, whereas if you're using transportation, petroleum products make more use because you have to carry the fuel with you as you go. So coal is easy for us to obviously haul fuel by a train, which is the most cost-effective way to move the coal. We get there, we generate the electricity, and then we just send the electricity out on the power lines. When we look at any kind of transportation, which is a huge portion, if you remember from, I don't remember if it was 101 or 102, we talked about transportation and how much of our energy use is based on transportation. That's typically where we use oil, whether it be gasoline, diesel fuel, something like that. Those are our two common fuels that we use. But we can look at vegetable oil, because vegetable oil is actually very, very close to diesel fuel, and it's not like this is a new idea that we've just started in the past 20 years or 30 years or something like that. Actually, when the very first diesel engine came out back in 1895, Dr. Rudolf Diesel is the one who developed the diesel engine. It actually ran on peanut oil or vegetable oil, and that was our initial fuel because we were just starting to get into refining fuels and not, we didn't have all the science of refining down yet as far as what fuels worked best. But peanut oil and vegetable oil are something that we've been using for hundreds of years. We already knew how to do that, so it was a pretty logical fuel to use. A lot of the reason, though, that we got away from that, because you can say, well, why didn't we just keep on using vegetable oils? But we can actually get by refining the petroleum, we can actually get diesel fuel much cheaper than we can vegetable oils. In the collection, the processing, and everything is much cheaper to do it that way. But as usual, anytime we run into a crisis or a problem, we're looking for alternatives, and that happened most recently, or probably the most obvious one that made us take a second look at potential other fuel sources was the energy crisis in the 1970s. We had an oil shortage, a gasoline shortage. If anybody was alive during that time, there were long lines to the gas pump. There were gas stations that were running out of gas, and believe it or not, the gas prices jumped from 30 cents a gallon to 50 cents a gallon almost immediately. Caused quite a panic to pay 50 cents a gallon for gasoline because it had actually been under 30 cents for probably 50 or 75 years. So it was quite a shock, and people immediately started looking to other alternatives of how can we do this cheaper, and how can we do something that's here local, that I don't have to depend on some country halfway across the globe in order to get my fuel, to kind of get that independence back, and take it out of other people's hands. So we're looking at vegetable oils. There are two basic classifications that we look at. There are edibles, like sunflower, soybean, palm. That's stuff that you can eat. That's stuff that you might have in your kitchen for cooking. And then there's the non-edible oils, rubber seed oil, these castor oil. These are things that we don't, you're not going to find in your kitchen. It's not edible, not usable for human consumption, but is used a lot for industrial purposes. They use it soaps, paints, lubricants, all kinds of different products. We basically get them from 4 different categories. Down here we have cultivated oil seeds, which is when you're driving down the road. I know I've seen some in eastern Montana. You also see them in Washington State. As you're going over by Moses Lake, you'll see large fields of sunflowers. And it's kind of funny because they're not the sunflowers I remember growing up that were 8 or 10 feet tall, that were mainly just grown for the seeds. These tend to be much shorter. They're only like waist high, and they're much denser. Rather than planting in rows like corn or something, they're very, very thick, almost more like a hayfield when you look at them that way. But those are our cultivated oil seeds. We have perennial oil-bearing materials, coconut and palm. Both are trees, obviously, and that's where you can get oil from them. Derived oil-bearing material, cottonseed and rice bran. We can't get the oil directly. It has to be processed. That's what the derived means. We have to process it in order to draw the oils out of it. And then oil seeds, forest or tree origin. Rubber seed oil, again, we see that one again. That's our non-edible. I don't know how many people paid attention to it 2 or 3 years ago. I don't remember how long ago it was. They actually had a project going here in western Montana where they were trying to get diesel fuel out of beetle kill timber. And literally they had a system that was about the size of a semi-trailer, and they would take it out into the woods. They would pull out these beetle kill trees, grind them up into a to wood chips, something that they could work with. And I believe they used a pyrolysis method to cook them down, and they could actually get pure diesel fuel out of the beetle kill trees. The downside of it is, and I guess it's okay, we look at it as a learning experiment of how we're going to do things. Anything we start off with is never efficient from day one. And the big problem that they ran into in producing this diesel fuel was because of how the energy went into the system. And when you figure on transportation to take the machinery out to the woods to create the fuel, you figure the machinery used to harvest the wood, to chop the wood up into wood chips that are usable, some sort of a hog fuel that we can cook down to get that diesel fuel. The efficiency just wasn't there, and it turns out that it took about 3 gallons of diesel fuel, petroleum, to create 1 gallon of diesel fuel out of these wood chips. So obviously it's not economically feasible looking at it that way, but at the same time we have to start somewhere, and as a proof of concept to show that yes, we can get diesel fuel there, and we can look at the process, maybe we need to look at a different way to run the process. If that same system was run by wind power or solar PV or some other renewable type resource rather than petroleum, we could probably develop a system that eventually would become cost effective as a way to do this. So there all are alternatives, but the reason we don't necessarily jump on them is because they're not economically feasible at this time. So we need to look into characterization of vegetable oils, and what are they? And actually they're very similar when you start looking at petroleum products and you look at diesel fuel. They're very, very similar. And you can get into a lot of chemistry, and we're not going to dig into that too awful far. I think the important part to pay attention to is down here at the bottom of this column. The number of carbon and hydrogen atoms in the chain are what determines the qualities of that particular fatty acid. So that's the structure, that's the shape of it, and because of that shape, then that determines what characteristics it has. When we look at fuels of any kind, whether we're looking at vegetable oils or diesel fuels, they're all kind of the same. We're going to look at the properties as physical, chemical, and thermal properties. The physical properties are viscosity, which we'll talk about here in a few minutes, but it's tends to be pretty thick. The cloud point, that's the point where things start to thicken up, and they're not. You'll go from, think about if you're cooking some fries up in your deep fryer. When it's cold, the thing is a solid, right? The vegetable oil in there actually turns into a solid. When you start heating it up, then it becomes viscous, becomes a fluid, and it clears up. So it goes from being opaque and not being able to see through it all to being opaque. So that's what that cloud point is as it starts to thicken, but it has not solidified yet. Pour point, which is important, especially when you're putting it in vehicles that you have to pump through fuel lines, and flash point, which is a pretty big deal when you're trying to ignite it inside an engine. And one more thing before I change the page here. Oops, I want to take a look at this figure 2.1, and it talks about world oilseed production. And if you look, the vast majority of our oils come from soybeans. And even though we talk about some of the sunflower fields that we see in the western states and in the plain states, it only accounts for 7% of all the oil produced. Soybeans are obviously a really big factor in that. And just on a side note, for anybody that has an interest in it, one of the things about soybeans is, compared to a lot of other crops that you grow, soybeans are very hard on the soil. So that's why you tend to see them circulating different crops through their fields. And if you just ran soybeans all the time, you'd have you'd quickly deplete the soil in your field. Okay, so we've looked at the percentages where those come from. So we're back to the properties. We talked about physical properties. Now chemical properties. What is the chemical structure? And again, it depends on how that stuff is aligned. That's what the properties are. Acid value, there's all kinds of stuff. Sulfur content, which is a big one. You see, we made a huge jump in the cost of diesel fuel in the early 2000s. I want to say it was probably 2002, 2003, somewhere in there. We switched over to low sulfur highway diesel fuel, and the cost went up considerably. It used to be that for a given price on gasoline, diesel fuel was usually about 20 cents cheaper a gallon because it costs less money to refine it than it does gasoline. Gasoline's more refined. But as soon as we went to the low sulfur fuel, or the low sulfur content, it added in additional processes that had to be done to the fuel, and that's why now typically you'll see diesel fuel prices being slightly higher than gasoline, because we've added those processes back in. And then we have thermal properties, which are actually running in our engine is probably one of the more important things that we need to know. Those thermal properties are how much energy is in that fuel. When I burn it, what's going to happen, and how much energy am I going to get out of it? That's where those thermal properties really come into play. So if you look right here, we talked about early on the very first diesel engines actually ran on peanut oil or vegetable oil, and the characteristics are very, very close to that of diesel fuel. And we really like the petroleum-based diesel fuel because it tends to have straight chain structures. They give better ignition, and they have a higher cetane number. The cetane number is the burning point when the fuel ignites, and that's comparative to the octane number in your gasoline. If you run too low of an octane number in your engine, it'll cause it to knock. Diesel fuel is kind of the same thing, only it's a cetane number instead. But they basically do the same thing. So we say that has it. Well, if you look down here, quantity of free fatty acids predominantly affects the flash point of vegetable oils, and hence its ignition characteristics. So whereas we have a really good cetane number on diesel fuel, fairly high, it's actually fairly low on vegetable oil. So that's a problem that we need to get around. We have to be able to adjust to that and adapt to that, because our engines are designed to run on petroleum products right now. So we have to find a way to get around that. Kind of a big issue, in anything we've talked about in energy here, with vegetable oils having 10% less heating value than diesel. So it's not as energy dense as what the diesel fuel is. The reason is because of the oxygen content in the molecules. And here's where we talk a little bit more about the cetane numbers. And typically what you see, if you go to the gas pump, is about 40 to 45 cetane level on your diesel fuel. But you'll see vegetable oils actually run from 25 to 45. So we need to find a way to work with that. Viscosity of vegetable oil is an issue. That's the thickness of it and how well it flows. Again, we're talking about running it through small tubing and injectors into an engine, which can be difficult if the liquid is too viscous. It also has very large molecules with low volatility. What happens is, as it goes through that tiny little injector, because those molecules are so large, you get poor atomization, which means when it gets injected into the cylinder, it does not mix very well. The atomization is the mixing of the air and the fuel, And because it doesn't mix very well, you end up with incomplete combustion because you got these big chunks of vegetable oil, and they don't have time to burn completely. And somehow we got a page in here sideways. So turn your head a little bit and we'll take a look at it. Some of the ways that we can use vegetable oils in engines is pyrolysis. Everybody should be familiar with pyrolysis. It's the same chemical reaction. Well, it's not the same, but it is a chemical reaction by applying heat in the absence of air. So we're not adding any oxygen to the system. We're basically burning it minus oxygen. That's pyrolysis. 250 to 400 degrees Celsius. And when we do that, that chemical reaction actually breaks down the vegetable oil into different products. And you end up with gaseous liquids, gaseous products, liquid fractions, which are paraffins or oils, olefins, naphthenes, and solid residue. So basically you've cooked it down and it's broken apart into its different components. In the same way you burn a campfire and you burn a piece of wood, that's kind of pyrolysis in action, and you can watch, and if you ever watch the flame, it doesn't actually touch the wood. The wood is being superheated. As it breaks down in that chemical reaction, the gases that are released, the fuels, if you will, are released from the wood itself, and you'll notice there's a small gap between the piece of wood and where the flame actually starts, because the wood itself is not actually burning, it's those gases that are burning, where you see that visible flame. So we know if we do that, now we've separated off some gases, which is wood gas is what the Biomax electricity generation system runs on. It uses pyrolysis to basically melt down wood chips, and the gas that comes off of that is piped into a converted internal combustion engine, which is set up to run on that wood gas, and it runs the engine. That's the fuel for it. And then we're going to end up with some of that other stuff coming out of there. The liquids will actually go typically within the gas, so they're not too much of an issue. Your olefins, naphthenes, those things, and then your solid residue, obviously you're going to have an ash left over because you've cooked that wood down, but there's always going to be a percentage there of ash no matter what. And if you look at the chart right there on the accompanying page with this, it talks about the different ash contents. So if I were to burn, let's just take a look at peanut oil. 0.02% of weight is going to be ash. So no matter how complete I burn it, no matter how perfect the combustion is, I'm always going to have that 0.02% of the weight is going to come out as ash. So that's one way that you can look at, one way that we can use it. Another method to use it is microemulsification, and basically what that means is we're mixing it with something. We can take the vegetable oils and mix it with an ester and a dispersant, or vegetables and an alcohol and a cetane improver. Once again, we talked about that low cetane. We need to bump that up, obviously. So that's something that we can add in there. And we can mix it with, diesel fuel or not. We don't have to, but that is an option. One of the things that we can do is mix it with methanol, and it will perform pretty much the same as diesel fuel. You really won't be able to tell the difference from it. This kind of comes down to where we were talking about, very similar to creating the diesel fuel from beetle kill trees, though. There's two problems with mixing it with methanol. Number one is the cost. Methanol is very, very expensive. So it's not something, it works great in the lab, but the reality of doing that within, for our system, our transportation system, would be cost prohibitive. The other problem with methanol is very hygroscopic, which means it draws water. So you end up with water in your fuel, and obviously water and fuel don't mix. That's kind of hard on your engines. And then we also get to dilution, which is exactly as it sounds, and it's pretty straightforward. We can just mix our diesel fuel with our vegetable oil and get that appropriate mix to match up our system. We can use that. We can use solvents, or we can use ethanol. All different ways to thin it out. By doing that, we're reducing its viscosity, which means it's going to flow better. It's going to burn better. It's easier to ignite. And if we're using pure vegetable oil, it's going to take some modifications to the system. Whereas diesel fuel, that's what the system is designed around. Here's some results of a test of using it to produce electricity in the villages, where they had a good test subject where it was very easy to watch and see what was going on. The high viscosity, very thick vegetable oil, low cetane number, and a high flash point cause cold starting problems. So, in your automobile, probably wouldn't be a very good thing, because you can't go out there and just start it whenever you want to. Somewhere like that, where the engine runs continuously, or it's inside a building, it's a system that we can tweak and adjust on, and size isn't a factor. We can preheat the vegetable oil to keep it warm, or put additives in for the startability. High flash point of vegetable oil is lower volatility, which can be good or bad. Diesel fuel by itself is not all that easy to light either, but it's actually harder to light vegetable fuel than it is to light diesel fuel. So your fire risk is a lot lower. Because of the clouding and pour points we talked about. And I'm going to assume, probably, having spent a bunch of time in Alaska myself, a lot of the villages out there run on diesel fuel in western Alaska. Talking very cold temperatures. A lot of those places are above the Arctic Circle. So you can see some issues with cold and fuel storage, and how do we keep the fuel from thickening up or even solidifying. These are the problems they're talking about. The vegetable oils with the low cetane numbers. Again, we talked about that as being comparable to octane numbers in a gasoline engine. So you end up with knocking. You can use a higher compression ratio, but again, now we're talking about modifying the engine and the costs associated with that to increase the compression of it to reduce the knocking. Vegetable oils are of low oxidation stability, and hence form injector plugging and gum formation. So filtering helps a lot, but again, we're talking about those large molecules that don't flow as well, so it tends to gum stuff up. So there's some additional maintenance, either replacing or having to clean injectors more often than you would with diesel fuel. Probably not as big of a deal in your car, but when you depend on electricity, and these engines are being run 24 hours a day, 7 days a week, maintenance becomes an issue. It happens faster because of the amount of hours that they're running, and you can't just shut it down because people need electricity. So these are things that we have to work on. And poor atomization, again, because of the large molecule size, causes incomplete combustion, and so basically you have leftover fuel that slides past the rings down into the oil and causes dilution of your oil, which is going to cause engine wear, your ring sticking, oil dilution. You could have all kinds of problems with that. So those are just some of the issues that we run into. And we don't want to as a good trial basis, it's great to find this stuff out. But um, these are all issues that have to be worked around in order for us to say, okay, that's it. We're going to change over to vegetable oil and we're getting rid of all the diesel fuel. So I'm going to leave off for there. We're going to stop there at transesterification and we'll pick it up again on Thursday. Again, taking a look at the Moodle shell. We also have a quiz this week. I need you to get week 1's quiz done before you worry about this one. This quiz does not open until Thursday afternoon after class, and you have a week to take care of it. You've also got some homework this week, so get on that. If you guys have any questions, Brad's going to be back in town tomorrow night. He should be here for class on Thursday, and I'm in my office anytime, so feel free to drop by if you got any questions or concerns. And we will see you Thursday.